Yes, I see it perfectly.
Okay, that's great. This is work that has been done jointly with James Ben-Worrell from the University of Oxford. He's been my supervisor when studying for my master's degree there. And this paper was published based on the results from our work together back then. The topic is the topic is parametric model checking continuous time Markov chains. I assume that most of the audience knows at least the basics about continuous stochastic logic, continuous time Markov chains, and so on. But I'll just walk very briefly and fast through a quick refresher. First of all, the continuous stochastic logic, which we extended in this paper, and for which we have some conditional decidability results, is a logic which describes formal properties of continuous time Markov chains. This is the model that we have attacked in our paper as well. Just as a brief reminder, this is how the representation of a continuous time Markov chains looks like. The main idea is that you basically start in a given state, and you can transition in any of these with probabilities proportional to the outgoing rates, which you can see here. And then the continuous time part of it comes from the fact that before transitioning, you spend up some time in your current state, which is a stochastic variable, which is distributed exponentially with parameter given by the sum of all outgoing edges. So basically, this means like intuitively, the higher an edge has the weight, it means that you're most likely to jump there faster, like to give some intuition behind it. The logic which we have extended is, as I was saying, the continuous stochastic logic. It's very important to be able to model, to express formal properties about continuous time Markov chains, as they find wide applications in general. Some examples include, as I've mentioned, medicine, physics, chemistry, and so on. One of the original logics which we have tackled, called continuous stochastic logic, was introduced around 1999-2000 by Adnan Aziz, and this allowed expressing some quantitative bounds on certain properties of continuous time Markov chains. In fact, it consists of state formulas, which we can evaluate in states, and of path formulas, which can be evaluated along paths. Basically, the main operator, we're only going to talk about like the vanilla CSL, say so, which has the temporal operator until, which is labeled by a time interval. Basically, what the until means is that the condition before it is true until the condition after it becomes true, with the transition happening in that interval. To give a concrete example, this is how a CSL formula looks like. Just a refresher again. This formula basically says that with probability higher than a half, we're going to transition to state S3 somewhere in between time equals 0 and time equals 4. True is just a shorthand for like all the possible states. In here, in general, people who are familiar with it will notice that some work is done around labeling the states, but in here we have reduced for simplicity the labels to be the states themselves. So as you can see, this formula here, so we've got the path formula, which is true until 0 for S3. True, this basically asks for true to happen up to some moment in between 0 and 4, and then for S3 to happen at the instantaneous moment right after. As true is always happening, true is universally valid, then this formula just asks for us to get to state 3 sometime between 0 and 4. And the probability in front of it transforms this path formula into a state formula, which basically says that starting in this state, the probability for that path formula to happen is greater than a half. A basic problem in general in any formal logic is the model checking problem. So the model checking problem for CSL for CSL is the following one. So given a continuous time Markov chain, a state in the chain, and the CSL formula, is it the case that this formula holds in the particular state S? Adnan Aziz showed in his paper in 2000 that this logic is decidable. The model checking of this formal logic is decidable, the model checking problem. In order to do this, he had some transcendental number theory approach. He used the Lindemann-Weierstrass theorem. Basically, what he did was transforming all the probabilities that arise in there through an algorithmic process in some exponential polynomials. And then he had decidability results regarding our ability to compare those polynomials with rational values. Basically, he was arguing that those polynomials can take rational values at rational points, apart from trivial cases, which we were able to identify. So then if exponential polynomials are not rational at rationals, then they're certainly strictly greater or strictly lower than zero. So we can just proceed doing approximations until we know on which part of a threshold they lie. So his result was kind of standard for transcendental number theory. Still one of the first great results, I think, regarding model checking decidability in the field of formal logics for continuous time Markov chains. As you have seen in here, in the previous slide, what this formula actually asks for is whether there is the probability for us to end in the S3, which is the error state in here. So if this models a very simple system, we might be interested if there is there are high chances for us to get an error in the first 4 units of time of execution of this certain routine. However, there are some other properties. Actually, there are many other properties which can be expressed in CSL. In its vanilla version, it's quite simple. It's a quite simple logic. However, we have identified one which is not expressed, one property, a certain class of properties which is not expressible under any currently available extension of CSL. For example, let us take a look again at this continuous time Markov chains, which depicts the simple process we've seen before. Basically, we've got 2 routines with some probability, with some transition rates in between them, and then we've got the error state, to which we also have some smaller probability transitions. And we might wonder if there exists a certain instantaneous moment in between these 0 and 4, let's say, seconds. We're wondering whether there is a moment of length 0.1 seconds, which is, let's say, most dangerous for us. So does there exist like some interval, let's say 2.5, 2.6, or 3.2, 3.3, between which we can end up in an error state? Why is this important? Well, if we can find out that there is a particular time interval of a small unit of time, which let's say it's 0.1 seconds, if we find that such an interval exists and that it's dangerous for us that we will end up in the error state in that one, we can then proceed identifying it, and we can try to isolate it, or we can be careful with our systems in that particular time, small time fragment. So we introduced PCSL, which is the parametric continuous stochastic logic, which basically just extends the vanilla CSL I have talked about, with these existential quantifiers over the time bounds, which label the until operators. And we also define PCSL n to be the restriction of PCSL with at most n quantified parameters. As you can see in the formula up here, it is PCSL1 because we've only got one quantified variable, which is this t. Also, to see why this is useful, there is a more interesting example here. So suppose we have a system and we have a certain state formula, some specification in CSL or PCSL, which we want to hold with high probability, let's say above 0.8, before this time t equals 5. But we do not want this to happen like too biased towards any short period. So we do not want any continuous time period of length, let's say 0.1, such that the formula holds with probability greater than 0.2 within it. Again, this means that we want a formula to happen. We want a property to be satisfied, but again, we want not to have any particular moment which is biased toward it. This can again be modeled in PCSL, particularly in PCSL1, as we are again quantifying over only one variable by this formula here. So as you can see, we've got this formula which says that the probability to end up to have the property we want to happen, the probability is greater than 0.8, which is again this true until. And then we do not want there to exist any t in 0, 4.9 such that the probability of it to happen again is greater than 0.2. So these are the kind of, this is a particular class of new formulas that can be expressed in PCSL1 and which can be expressed in CSL. And after defining this, you can take a look at the paper and also to the pointed master to my pointed master thesis for plenty more examples and classes of properties. So we naturally had the question whether this PCSL model checking problem is decidable, as we know that CSL model checking is decidable. However, now we have this extra quantified variable, which make Adnan Aziz's proof from his original paper unsuitable anymore. As Lindemann-Weierstrass, the theorem that he used is not strong enough to deal with our case. And we introduced this PCSL model checking problem, very similar to the CSL model checking problem. The only difference is that right now we're not wondering anymore whether a state formula holds in a particular state of the Markov chain, but rather whether it holds given an initial probability distribution over all the states in the continuous time Markov chain. So this is its definition. We've got again a continuous time Markov chain, a distribution pi with rational entries over the states of M, and the PCSL formula. And we want to answer the question whether it holds given our continuous time Markov chain and the initial probability distribution. So now we're not talking anymore about state formulas, rather about probability over states formulas, but states can easily be encoded in it by just having pi beyond one hot encoding of the state. We want to
Only 2 minutes left, maybe a little bit less than that.
Sure, thank you. And then the model checking problem for PCSLN is just this, is still the model checking problem for PCSL, but now we restrict the existential quantified variables to be at most n. The main contribution, the main technical contribution that we had was showing decidability of the model checking, the one parameter fragment of PCSL, so that's PCSL1, assuming Schanuel's conjecture. Schanuel's conjecture is, let's say, a stronger version of Lindemann-Weierstrass, which Adnan Aziz used in his proof. It is widely used nowadays in conditional decidability proofs. However, it is known like to be a very strong result, and there are attempts for it to be proven, but it's still not. However, there has been work done by Ziebler and others using Schanuel's conjecture, and it seems to be a good fundament for hard decidability problems. We showed that the decidability of the model checking for PCSL1 holds using this result. And in fact, in order to show it, we reduced it to the positivity problem for exponential polynomials, which is a known hard problem from a mathematical point of view, as it doesn't have any results, any unconditional results. It's basically asking for a class of real valued exponential polynomials, such as you can see in here, whether they're strictly positive at some point in between two given rationals. We proved conditional decidability of the positivity problem, assuming Schanuel's conjecture, and then we showed in turn that this implies conditional decidability of the PCSL1 model checking problem. Talking about...
I have to ask you to come to the conclusion.
Sure. So I won't go over the technical details here.
I'm sorry, it's time constraint.
Yep, sure, no worries. We have also shown that our problem in its unrestricted version is a hard one. Again, we managed to reduce the threshold problem for matrix exponentials, which is equivalent to the positivity problem for exponential polynomials. We reduced it to the model checking decidability of our problem. And therefore, we showed that an unconditional decidability result is very hard. So we can't hope for that. Therefore, in conclusion, we introduced this extension of CSL, which is a powerful parametric logic for expressing this kind of temporal properties of continuous time Markov chains. And then we showed that the decidability of one of its strong fragments, PCSL1, holds under Chalmers' conjecture. And also we showed that its unconditional decidability is very hard if we look at it in an unrestricted way without any conditions. So yeah, this is it.
Thank you very much.
Thank you.
Thank you very much. We have a couple of minutes left for any possible questions. I myself have a couple of them. Okay. First, I would say that these logical formalisms have quite a bit of an overlapping with the fuzzy version of logics, in which instead of talking probability, you have quite a bit more general setting, and your formula are not just true or false, but they are true to a certain degree. So my question would be: have you ever looked into that? Maybe for Markov chains in some fuzzy version of this logic, and what do you have to say about that?
Yeah, that's interesting. No, we haven't looked into it. We've mainly been, let's say we've mainly been focusing on the underlying mathematical problems, the decidability of the positivity problem for exponential polynomials and so on, which were open problems. And then we found this logic to be rather suitable for them, but we haven't explored fuzzy logics.
And when you say that the problem is hard, you mean NPR, I understand.
No, so yeah, so maybe that's a point that I skipped when talking. I hope I made a mark of it on the slides. So by hard, I mean not hardness from a computational theory point of view, but rather from a mathematical point of view, as in we do not have any unconditional results about them. These are open problems.
So you don't know what is the exact computational complexity of the problem?
Yes. And in general, this kind of positivity and threshold decidability problems are either trivial to classify as p-space complete or anything, or it's not even know if they're decidable at all. So it's not been like our main scope to find out if we can fit the decidability into any class, but rather to see if it's decidable at all or not.
Okay. Thank you very much again then for the nice talk. Is there any other question? If there is no,
thank you.
Okay.